Hello guys, this is CodeNCode and this is the third lecture of this tree query series. And in this lecture we are going to see how we would apply Moore's algorithm on subtree query problems. So for that we have chosen this problem, codeforces d1d problem, which is rated 2400. So this is the problem. I tried to find many other problems which required queries on subtree, but could not find some easier problems. So I wanted to find an easy problem so that I can show you the implementation, so that you can apply that on harder or tougher problems on your own, but wasn't able to find such problems. So the only problem I find was this, which is d1d problem, and it is rated 2400. So let's get started. So the problem is simple. So the problem is we are given a rooted tree which is rooted at node 1, and each node is given a color C. So there are m queries, each query of two type, vi, vj and kj. So this is basically jth query. So v and k, v is the node number and k is a special thing I'll tell you. So v is the node number. So in the subtree of v, we would see how many colors are there which are appearing at least k times. So if I show you with an example, this is the first test case. There are 8 nodes and 5 queries. This is the color of each node. Node 1 is having color 1, node 2 and 3 are having color 2, node of course 4 and 5 are having color 3, you see, and so on. So now there are 7 edges, of course, because this is a tree and with 8 nodes, so there are 7 edges, and these are the last 5 queries. 1 2 means in the subtree of 1 how many colors are there which are appearing at least 2 times. So you see, we won't count 1 because 1 is appearing only 1 time. Color 2 is appearing 3 times, so we would count this. So there is 1 color at least, and color 3 is appearing 4 times. So color 2 and 3 are appearing at least 2 times. So the answer of first query is 2, you see. Now 1 3. So in the subtree of node 1, how many colors are there which are appearing at least 3 times? So again the answer is 2, because 2 and 3 both are appearing 4 times. So the answer is 2. For the third query, it asks in the subtree of 1 how many colors are there which are appearing at least 4 times. So the only answer is 3, because color 3 is appearing 4 times. So the answer is 1. There is only one color which is appearing at least 4 times. So second last query is 2 3. So in the subtree of 2, how many colors are there which are appearing 3 times? There are no colors, as you can see. In the subtree of 2, these are the nodes, and only 2 is appearing only 2 times, 3 is appearing only 1 time. So there is no color which is appearing 3 times at least. So the answer is 0 for this test case, and similarly for the last one the answer is 1. So this is the frequency array. If you are aware with Moore's algorithm, in the previous lecture also I have explained how to answer subtree query with Moore's algorithm. So first of all, what we are going to do, we are going to flatten the tree, then we would have starting time, ending time of each node, and we would also have flat tree array. After that, to answer a query of a particular node for its subtree, what we would do, we would left and right for that query. For example, if you see for this query 1 2, 1 is the node, so we want the subtree of node 1. So starting and ending time of all the nodes in the flat tree from index is starting time of 1 to ending time of 1. All of those we would add. After adding each of the node which is appearing 2 times, that is the node which is appearing in the subtree of node 1. So I have already explained this in the previous lecture. So first thing, let's go and apply the flat tree and all. So this is max n because the number of nodes are 10 to the power 5. So this is 10 to the power 5 plus 1. So that we have indices from 1 to 10 to the power 5. Now this is block size, of course roughly square root of n. This is adjacency list for graph. This is starting time, terminating time, flat tree array, and this is a color array. So these are required fields. After that we have node frequency. Node frequency because this, let me show you, because of this. Suppose I wanted to find the answer of subtree of node 7. So what I would do, the query would become L would be starting time of node 7 and R would be ending time of node 7. So in between this range, all of the nodes which are appearing exactly 2 times are the part of subtree of 7. So you see 7 is appearing 2 times, 8 is appearing 2 times, 9 is appearing 2 times. So 7, 8 and 9 are the part of the subtree of 7. So this, where we are, node frequency would keep the frequency of the node. So whenever the frequency of node becomes 2, we know that, oh okay, this node lies in the subtree of current node for which we are adding all these elements. Is the element frequency. Element frequency is nothing but the frequency of color. This is this thing. So if you apply for node 1, so what you would do, in the range starting time of node 1 to ending time of node 1, you would add all of the nodes. Whenever the count of node becomes 2, which means this is appearing 2 times, which means this lies in the subtree of 1, and hence we would increment the frequency of that color. So you see, color 1 is appearing 1 time, color 2 is appearing 3 times, so 1, 2 and 3. Color 3 is appearing 4 times, so, and color 4 is appearing 0 times. So this is the color frequency, or I like to call it element frequency, and that this is frequency of frequency. Now why it says so? So suppose we added the whole elements and whole subtree of node 1, and the frequency array looks like this. Now the query comes, okay, tell me all of the colors which are appearing at least 2 times. So what you would do, in the frequency array from 1 to n, you would go to every single place and see if this color appears if this color appears at least 2 times or not. So you would go to index 1 and you would see whether color 1 is appearing 2 times or not. The answer is no, because color 1 is appearing 1 time. You would go to 2, color 2 is appearing at least 2 times, because color 2 is greater than 2, right? Frequency of color 2 is greater than 2, so we would increment the count. Again we would go to 3, color 3 is appearing 4 times, which is greater than equal to 2, so we would again increment the count would become 2, and you'd come here, color 4 is appearing 0 times, so we won't increment the count, so the count becomes 2. Now you might wonder why I have taken a frequency array of colors to node 4, to 4. Actually I have to take a frequency array till node 8, because the color can be as large as 10 to the power 5. Color of each node can be as large as 10 to the power 5. So it is possible that the color of node 1 is actually 10 to the power 5 and the rest of same. So it doesn't matter whether the node numbers are only 8, the color can still be 10 to the power 8, because here in the let me increase the font size. So it doesn't matter whether the node numbers are 10 or 12, it doesn't matter, because each color can be as large as 10 to the power 5 and it is independent of n. So it doesn't matter whether the node numbers are only 4, the color of first node may still be 10 to the power 5. So the frequency array must be of 10 to the power 5 size. So you see, even after adding all of the nodes of a subtree, so suppose we were answering for this, so we would add all of the nodes, all of the frequency of this, so frequency array would look like color 1 would be 0, color 2 would be 2, color 3 would be 1. But still we are unsure when we are going to check, okay, in the subtree of 2 how many elements are there whose frequency is at least 3. So you would still have to go from node 1, color 1 to 10 to the power 5, because we do not know what color is appearing in the subtree of 2, and each color can be as large as 10 to the power 5. So we have to traverse the whole frequency array from 1 to 10 to the power 5. That is a big loss in terms of time. So what we are going to do, we are going to create another frequency array, which is frequency of frequency. So what this would store, it would store the frequency, how many times ith frequency appearing in the frequency array. So how many times are there, how many colors are there with frequency 1 in the frequency array? There is one color only, so that is why there is only one element with frequency 1. That is why at index 1 frequency of frequency we are having 1. Now how many elements are there in the frequency array which are having frequency 2? There is no element. That is why frequency of 2 is 0. How many elements are there with frequency 3? 1. How many elements are there with frequency 4? 1. So this is frequency of frequency. Now if I want to answer for query 4, so what I can do, I can directly start from index 4, because these represent the element which are having frequency 3, and we are not interested in the element which are having frequency 3 or 2 or 1. We are interested in the element which are having frequency 4 or greater than 4. So we would directly start from 4 and go till n, which is 10 to the power 5. So we would go till 10 to the power 5. Now the problem you see here is also the same as this. The problem is we still have to go till 10 to the power 5. But there is one more thing. I can apply some query some technique and then get answer from here to 10 to the power 5. In if you are using say segment tree, then you can get the answer in log n time, but the same you can't do for this. For this I can do from start. I know that starting from position 4 to 10 to the power 5, all of the elements which are appearing, some of them must be the answer, because all of the elements are having frequency at least 4, right? But here you can't do that. If you are working for frequency say 3, so this element doesn't lie in the answer, because this element is having frequency 1. This element would be added in our answer because this is having frequency 3. This would be also added, but this won't be added. So I cannot be sure that okay, what elements are there which would be added in my answer. I'm not sure from 1 to 10 to the power 5 in the frequency array which element I would add. You see, first element I'm not adding because the frequency is not 3. Second and third I'm adding because these are having frequency at least 3. Again, fourth element I'm not adding. So from 1 to 10 to the power 5, I'm actually not sure which element would be added in my answer and which element would not be added in my answer. So I do not have clear idea that what is the range which so that I can apply range sum query on that. In the frequency array, you won't have that surety, but in frequency of frequency array, you actually have that surety because all of the elements, if we are working for 4, we know that starting from 4, if any element appears, then starting from 4 to 10 to the power 5, if any element appears, then its sum is directly will go in the answer. And these from 1 to 3, these won't be added into the answer. So we are 100% sure that the frequency sum from 4 to 10 to the power 5 will be added in our answer. So I can apply range sum query here, but there we are not sure whether which element would be added and not. So we are not sure, so we cannot apply any range sum query on frequency array. That is why we are having frequency of frequency array. So this is frequency of frequency. This is the answer array. Of course, if you are aware of Moore's algorithm, since the queries gets reordered, so we must have the answer array to answer each of the query, to store the ith query. This is and nothing new. This is the timer. So the first thing we would do, we would read all of the colors. First of all, we would read n and q because this is the input, and then we are running a loop till n. This is a for loop which runs from 1 to n. So I'm working with 1 base index system. We are reading color of each element or each node, and then we are running a loop from 1 to n-1 because there are n-1 edges in the tree. Basically we are reading the edges. So we are reading A and B. In the adjacency list of A, we are inserting B. In the adjacency list of B, we are inserting A, because this is a undirected graph, undirected tree. After that, we are initializing the timer to be 1, and we are running a DFS to flatten the tree. So you see, in the DFS, oh yeah, this is important. This is query structure. Since each query is having L, R and K, also the index, because you need to have the index so that you can restore the answer, because all of the queries would be reordered after the sorting. So here I have defined a query array of size 10^5. So after defining timer to be 1, we are doing nothing but applying the tree flattening thing that we have already studied in lecture 1 or 2, I guess. So I'm not going to explain this thing, because I have explained this thing in greater detail in lecture 1 or 2. I don't actually remember, from the same series. So after running DFS, we have a flat tree. After having flat tree, we have starting time, terminating time of the node. So after that, we are going to read all of the queries. So this loop would run from 1 to q, of course, because there are q queries. Each time we are given the node number and the k. So L and R, as explained earlier, would be starting time of A and terminating time of A. After that, one more thing, if you have no idea about Mohs algorithm, then these lecture series are not for you, because this is Mohs algorithm is actually prerequisite for this series. So it is important, go and check out the Mohs algorithm, because if you have no idea about Mohs algorithm, then try to learn Mohs algorithm on tree is actually time wasting. So just go. If you have no idea about Mohs algorithm, I have explained Mohs algorithm in my square root decomposition series, so go and check that lecture first. So L would be starting time of A, R would be terminating time of A, and K is of course K, and index of current query is I. After that, we are sorting the queries. So since I am working with one base index system, that is why base address +1, and there are total number of elements, that is why also adding q. So this is starting, this is ending position, and this is the comparator function, which we have already seen in the Mohs algorithm lecture series. So if this is the block, this is the starting block, and this is the ending block. So sorry, this is the starting block of A, and this is the starting block of B. If they both lie in the same block, then if they do not lie in the same block, if both the queries do not lie in the same block, of course we are sorting by the block number, because the query which is having smaller block size would be placed earlier than the other one. Otherwise, if they are in the same block number, then we are sorting by right pointer, depending upon the parity of the first query's block number. So this is a comparator function. After sorting all of the queries, all you have to do is apply Mohs algorithm. So this is left pointer, this is the right pointer. For each query, we are getting the left, right range of ith query, the index of it, and the k for the ith query. After that, this is the standard Mohs algorithm thing that we do. We have 4 loops, 2 to expand, 2 to reduce the range. The important thing in any Mohs algorithm, once you know the Mohs algorithm, the only important thing in the next lecture becomes the add and the remove function, because this is like the template for Mohs algorithm. We take the L and R of the ith query, and then we run these 4 standard loops, each time adding if you are expanding your current range, and removing if we are reducing the current range. So everything you need to change is only for each problem, only thing that you need to change are only the add and remove functions. So let's go and see this add and remove function. So MR is actually the index in the flat tree, because L and R are also the index in the flat tree. So if we see add, now what we are going to do, suppose suppose I want to answer the query for node 7. So starting timer is this and terminating timer is this. So I will start adding the elements. Initially my range contains nothing, so I would first add 7, then add 8, then add 8, then add 9, then add 9, then add 7. So once our range contains all these elements, the answer would be, the answer you know in a moment. First let's show how we add this. Whenever we are adding an element, we are given the index in the flat tree, then we are taking out what is node at the ith index. So from the flat tree, what is the ith what is the node at the ith index? This is the node and this is the color of that node. So color array contains the color of that node. So this is the node, this is the color. After that, what we do, we increment the frequency of node. So you need to do this because once you were, suppose you added 8 and then you are going to add 8 again. So in the range we see the elements are appearing twice. So that is why we must know the frequency of the node. So when the frequency becomes 2, so it becomes clear that okay, this node is the part of the current node's subtree, right? So that is why when the frequency of the current node becomes 2, then is the time when I would add its color into the color frequency array. So when the frequency would become 1, then I would not add. So you see, when we added node 7, actually its frequency becomes 1, right? When we went to so we would do nothing because I am adding a node. I am updating the node's frequency in the frequency array if and only if the frequency of that node becomes 2. Frequency of node becomes 2 means that this node lies in the subtree of the current node for which we are applying the Mohs algorithm query. So basically you have to add only once. In the whole range, the node would appear 2 times and you have to add only once. Either you can add when the frequency becomes 1 and you should not do, in that case you should not add when the frequency becomes 2 because you have to add only once. Or what I'm doing, I'm adding only when the frequency of the current node becomes 2. So when the frequency of node 8 or 7 would become 2, then it indicates that okay, this part of the subtree, so I would increment the frequency of current color. So I am incrementing frequency of current color. Now frequency of frequency array, the initially if the frequency was say 1 of the current color is say 5, so frequency of 5 initially was say 1. So if the initial frequency was 1, then in the frequency array at position 1 this was incrementing, right? Because each frequency contributes in the frequency of frequency array. So initially of the current, if the current color was having say frequency say 1, so in the frequency array at index 1 it was incrementing or adding 1. But now the frequency of this color has changed to be 2. So what you would do, current frequency is this element frequency of C. So at this index, so initially say frequency was 3, now the frequency is 4. So at index 4 we would increment it and at index 3 we would decrement it because initially it was adding in index 3 because its previous frequency was 3. So in the previous frequency we are removing it from the previous frequency and now adding into the new frequency. So initially if this color was having frequency 2, so and the new frequency is 3 of course, so in frequency 3 in FF array at index 3 we would increment because this is now transferred from having frequency 2 to 3. That is why in the frequency 3 we would add, or basically in the new frequency of the current color, new frequency at index new frequency we would increment and the previous frequency we would remove. So this color has transformed from having this frequency to this. That is why the previous frequency must be removed in the frequency array, FF array. So this is how we apply the add function. Now to remove, of course, since I am adding the node when the frequency of node becomes 2, right? Here, if the frequency of node becomes 2, then I am adding. If while removing the frequency, what you would do, you would take the node, you take the color, you decrement the frequency of current node, because you are removing this color, this node. So the frequency of current node would decrement, right? Now the frequency, I am adding the node when the frequency becomes 2. So if the frequency of node becomes 1, then of course I would remove it. So if the suppose the frequency of the node was 2, which means I have added it into the result, but now we have removed the second element, so now the frequency has become 1. As soon as the frequency becomes 1, which means I need to remove this. So to remove it, of course the current color would be removed. Same story again, in the frequency array, at the new frequency I would increment, and in the old frequency I would remove. So this is what we are doing in the remove array. So after doing all of this adding and removing function, now we would have finally have this frequency array. So now suppose after adding the whole subtree of node 1, this is the frequency, this is the frequency array, and this is the frequency of frequency array. Now to answer for 2, when k is equals to 2, we start from position 2 towards the last element, which is max n. So get answer function would return the sum of the frequency from starting from position k towards n. I do not know why I have taken n. Instead we have to go till max n. The reason, again, because each node, okay, yeah, this here it would be n. We don't have to go till max n. Reason, see, the frequency of frequency array keeps the actually keeps the frequency at ith position, say in position 10 in the ff array. In the position 10 we would have 1 or 2 or 3. If at position 10 in the ff array we are having say 3, so that indicates that okay, there are 3 colors in the frequency array which are having frequency 10, right? But in the frequency array here we need to go till 10 to the power 5, because we do not know what can be the color of element. But here we don't have to go till 10 to the power 5, because it keeps the ith, the 10th index of ff array would contain any positive element if any color is having frequency 10. So each of the node, the whole node, the total number of nodes are only n, so there would be not a single color which would have frequency more than n, right? So if there are 8 elements like this, and all of them are having color say 1, so after adding all of the elements, the frequency array would look something like this. At position 1 we would have 8, for the rest we would have 0, because color 1 is appearing 8 times. Okay, so at max in the ff array we would have positive results saved at index till 8 only, because at max the frequency of any color can be as large as the total number of nodes. So you see here we needed to go till 10 to the power 5, which is the highest number of color, but here we only have to go till n. So that is why we are get answer function would return the total number of basically the sum from index k to n. So the get answer function is very simple. As you can see, answer is equals to 0 starting from index k till n. In the ff array we are simply adding the ff of I and returning the answer. So if I show you by running an example, this example, we see the answer is 22101, which is 22101, which is the answer of the first test case. For the second test case, answer is 4 only, so let's run this. You see the answer is 4, but you see there is a problem, and the problem is this. First, if you submit the same solution as discussed now, this is what you are going to get. This is the thing that you are going to get, that is TLE on the 13 test case. Because the most expensive operation of the whole thing, for each query what we are doing the standard most thing, which is okay. Each element add and remove function actually work in constant time, because to add, all we are doing, we are incrementing the frequency, decrementing the frequency. That is the whole thing that we are doing. So add and remove function are actually working in constant time. So this is standard Morse algorithm, and the complexity is q square root of n. But this operation, this to get the answer, where for now we needed to find the total sum from k to n, and this is the most expensive what we say operation. Suppose there are q queries. Each time, suppose I'm asking for k is equals to 1. So if there are q queries, then this get answer function will be called q times, and each time, suppose for the worst case, I design the test cases such that k is equals to 1 in each query. So in each query we are running a loop from 1 to n. You see, the get answer function is running from k to n. So if you put k is equals to 1 to design a test case which runs in worst case, so if in all of the q queries I give starting time to be k is equals to 1, so the overall complexity would become q square root of n plus q times n, which is basically q into n, which would result into the TLE. So this, in the next lecture, I will show you how you can actually optimize and get this from this, because I wanted to give you an assignment so you guys can yourself think something to optimize certain code. So this function we are using as a subroutine. So this function returns the sum from the frequency array from position k to n. There are a lot of what we say range sum queries. So if you apply more segmentary, then from k to n, of course you can answer in log n time, right? So the question is what range sum query you are going to apply to reduce the running time of this function from big O of n to anything smaller than that. And you might see that here I'm getting TLE right 1 2 3 4 5 times, and I had applied something which I thought would reduce the complexity without going into the calculation of complexity. So this is a really good this would be a really good experience for you to reduce the complexity of some of the subroutines that we are using. So we are using that get answer function as a subroutine. So you go and apply some of the range sum queries like square root decomposition or segmentary, or we have binary index tree or Fenwick tree. So just go and apply some of the range sum query and try to reduce the running time of this function, because this function is what giving us TLE. Once you reduce that complexity of get answer function, then you reduce the complexity of the overall algorithm. And here we are doing nothing but simply printing the result of each answer. So I'm giving the link to, I'll be posting the link in the description of this solution so that you can take this solution and update your get answer function. In the next lecture, I'll see how we can actually reduce the complexity of this get answer function. So this was all for this lecture. I hope you guys have got something from it. And if you have any query or doubts, you can of course comment it out in the comment section. So thank you guys for watching. Until the next video drops, keep coding. Thank you.